Setting up the Mongoose web server. In this video, I will show you complete step-by-step process of integrating Mongoose, which is an embedded web server, into your STM32 projects. And in this video, I will use this Nucleo board, and this one is based on STM32 F439 and it has inbuilt Ethernet. So this microcontroller, this STM32 F439, it has this Ethernet peripheral built in. The MAC is built in and we don't have to use any external Ethernet controllers like ENC28J60 or W5500. We just have to use a PHY chip and we can get the direct output in this RJ45 connector, Ethernet connector. We can directly connect the Ethernet cable here. So I will use this board for showing you how to integrate Mongoose in your STM32 projects. So now let us begin. Open your web browser and go to mongoose.ws. This is their official website. So the very first step is getting Mongoose. So here from the top menu, just go to the GitHub Repo like this, and from here code, just copy this URL and go to your system drive, and here you can create a folder for Mongoose. So here I have created a folder for Mongoose. Just go inside that folder, something like this. Right click here and open git bash here. So git must be installed on your system and I will have a dedicated video on that. Please go and watch that video. It is not covered in this video. So it will open up a command prompt like this, and just here use the git clone command and here paste the URL, something like this, and hit enter. It will clone Mongoose on your local computer or on your local disk. Now Mongoose is here. So here is the entire repo cloned in your local drive. To make integration easier, they have used amalgamation method. So in this amalgamation method, various C source files are amalgamated or compiled into a single C source file, and this single C source file can be added in your reference project and it will include everything. Everything is here inside these two files only, that is mongoose.c and mongoose.h. So to add Mongoose web server support to any of your STM32 project, you just need these two files. The network drivers, the TCP/IP stack, and the higher level, the HTTP web server, everything is packed inside these two files only, and you have to add only these two files to your reference project. But here also you will see one more directory, that is SRC. This is the standard source directory. If you go inside this, you will find various C source files like this. So actually these files are used for development, and different parts of the stack, different part of this web server, they are kept in separate files, so they are easy to manage. But you don't have to add all these files to your project because these are already amalgamated into a single source file using some amalgamation tools. So you don't have to use these files, so they are just for reference or just for development. You don't the contents from these files only, like the DNS, the base64, the flash fs, the JSON handler, MD5 thing, network interface, over there updates, OTA supports, SHA support, socket support, timer support. So everything, the contents from these files are amalgamated into these two larger source file. So you can notice here, you can just notice the size of this file. So this is very huge, 681 KB. The reason why this file size is so big, because this is the amalgamation of all these source file. But you don't have to fear that this is a very large file, it will not fit into your microcontroller, because these contains everything. So only the selected features from this file goes into your project, not everything. Some like these file contains driver for W5500, it contains driver for TI's microcontroller, it contains the various types of driver for various different kind of microcontroller, but only the selected microcontroller, the microcontroller which we have selected through preprocessor directive, only the driver for those things goes into your project. They are other things are excluded and are not compiled into the project. Start STM32 Cube ID, and it is better to use this version, that is version 1.16. Go to the file menu, select new and STM32 project. Here enter the part number of the microcontroller, that is STM32 F439. Here is the microcontroller of our choice. Just click next. Enter the project's name here. We will start by creating a template project. By template project, I mean a project that can be By template project, I mean a project that can be later used to derive other working projects, and it will be a reference project, so you don't have to create. So every time you do so every time you need Mongoose support, you don't have to repeat these steps. That is why I will create and keep a template project. So that is why I will use a name. So that is why I will use a name like this. Notice the word template here. Click next. Click finish. So this is the STM32 Cube GUI configurator, and we will start configuring our project from here. The first thing that we need to do is to go inside this system core section, and here we have to configure the RCC, and this RCC stands for the reset and clock controller. And first we have to select the high speed clock source. By default it is disabled, but here we have to select this option, that is bypass clock source. And why we are selecting this option, I will discuss. And second thing, this is the low speed clock. This one is used for the RTC or the real time clock. We will also enable this because we have this crystal oscillator soldered on the board. Now let us select crystal ceramic resonator here. Just a moment. So here in this project we are using this Nucleo board. This is STM32 F439 Nucleo board. So we have to open the user guide of this board, and here I have that user guide or the user manual. This is very important document, and the ID of this document is UM1974. So you can search this manual on the ST's website, and after downloading this we can go through this. So now I will tell you why I have selected bypass clock source here and not crystal ceramic resonator. The reason is that this board, this Nucleo board, so this board, it does not come with this external oscillator, main oscillator. The space is there in the PCB. Here you can see the space is there for X3, but no actual part is soldered here. And also this solder, this SBs, this stand for solder bridge. So solder bridge, these two solder bridges are not sorted, so this microcontroller is not connected to this crystal oscillator. And also these two load capacitors, that is the C38 and C37, they are also not populated in the PCB. But as you can see, this low speed oscillator which works for this RTC, it is soldered there by default, but this one is not soldered there, so we cannot use external oscillator with this board. If you want to use this external oscillator, you have to solder these parts manually here by yourself. But currently we are not using this. So how this microcontroller is getting the clock? So this microcontroller is actually getting its clock pulses from the top section here, the ST-Link section. This one, this ST-Link is providing the clock source through the MCO pin. So this microcontroller, it is providing a single clock pulse to this microcontroller, our main microcontroller. And to use this kind of clock pulse, this is actual clock pulse and not a crystal oscillator. This is means proper electrical signal. The clock signal, it is coming from this microcontroller to this microcontroller, and we are not using this crystal oscillator. That is why we are using bypass mode here. And one thing you have to note, that this ST-Link, this provide a fixed 8 megahertz clock source to this microcontroller. So this microcontroller is providing 8 megahertz clock signal to this main microcontroller. So while configuring the this clock, when we will go to the clock configuration section here, we will enter 8 here, because we are getting 8 megahertz from the ST-Link part. Now let us move on to the next configuration, and this time we will go to the SYS or the system section like this. So by default this debug is disabled, we have to enable it, and here we have to select this, not the JTAG interface, we have to select the serial wire interface, because our development board is using serial wire for debugging. And one more important thing here we have to do, we have to change the timer which is used for the time based source. And here we have to, I will select this timer 6 here. You can also select timer 7. So this timer 6 and timer 7, they are the basic timers. That means they don't have these output compare PWM, those kind of features. So these are the simplest timer. And the time based source, we can use simplest timer. We do not have to waste one of these advanced timers. That is why we will choose either timer 6 or timer 7. And you can learn about these timers from the data sheet of this microcontroller. So let me open the data sheet. So here I have the data sheet of my microcontroller, that is STM32 F429. So here I have to go to this section, functional overview, and then I have to go to the timer and watchdog section, where it is watchdogs and timer, or timers and watchdogs. So here it is, timers and watchdogs. So here if we compare the features of various timer that is available on the microcontroller, we have to go to this section, that is timer feature comparison. So here they compare, they have given a whole table, it is table 6. So here you can see on this table that we have advanced control timer, these are the most expensive kind of timers, and it is timer 1 and timer 8, they have most features available. And then comes the general purpose timers, they comes after this advanced control timers, so they also have lots of features. But finally we have this basic timer, these have the least number of features available, so these are the most simple timers. So it is better to first use these timers for this simple application, and uh, if we do like this, then all these good timers, these feature rich timers, they will be available for our later use for some other advanced application. That is why I have chosen timer 6 or timer 7 for this time based application of this HAL layer of the cube ID. So where is timer 6? Here it is. So now these HAL libraries, the ST's HAL or the hardware abstraction library, they will use timer 6 for simple this time based source. That means for the delay purpose we use functions like HAL delay. So it will use this timer for this calculations for the timekeeping purposes. Now what is the reason that we are changing the default timer here? By default it was SysTick, and we have changed this to TIM6. So why we have done this? Why we have done this. So the main reason is that this project is going to be a free RTOS based project. So this project will not be a bare metal project, but it will be running over an operating system, a real time operating system, that is free RTOS. And this free RTOS also needs a clock source for its main scheduler, or this for preemptive multitasking. It requires a timer, and generally the best timer to use with free RTOS is this SysTick timer. So we are using this SysTick for our, that is tick source for our free RTOS real time operating system. That is why we are using TIM6 here for HAL libraries. Now let us configure the clock. So go to this clock configuration section, and here we have already entered 8 because we are receiving 8 megahertz signal from the ST-Link MCO. And here we have to change the this clock source for our PLL. By default it is coming from the HSI, or the high speed internal clock source, but we will switch this to HSE, or the high speed external clock source. So now we are receiving 8 megahertz to the input of our PLL. This is the main PLL, and then we have here we have to divide this clock source by 4 actually. So in this way, here at this point we will get a 2 megahertz signal, and we will multiply it by 180. Here, and finally we will switch this main clock. This is system clock mux, or the multiplexer. So this is the system clock. Currently by default it is getting a direct signal from the HSI, or the high speed internal. We will switch it to the PLL for high frequency operations. So you will get, we are getting 180 megahertz here, and this is also the maximum clock speed that this microcontroller supports. So our H clock, it is 180 megahertz. But here we have some problems. That is our two of our peripheral clocks, that is peak clock 1 and peak clock 2, they are getting overclocked. So the maximum this our first peripheral bus, that is peak clock 1, it supports, here it is written that it can go maximum only up to 45 megahertz. So here we have to divide this by 4. So now we are getting good 45 megahertz here. So this is the slower peripheral bus, and all the slower peripherals are connected to this bus. This is APB1, or the advanced peripheral bus 1. And next we have a better peripheral bus, and to this peripheral bus all the high speed peripherals are connected, and the maximum clock frequency of this peripheral bus is 90 megahertz. So this time we have to divide this by 2. In this way we have properly configured our clock source. Now let us save the project by going to the file and save all option. Now moving on to the next item, we will go to this connectivity section. Here we will enable our this UART3, this one. So we will use this for debugging purposes. We will use printf style debugging, where we will print messages to show the progress going inside the microcontroller, and we will use a terminal program to view those messages on our PC screen. So here we have to select USART3, and we have to use the asynchronous mode. It will enable the UART, but we have to change the pin configuration. So by default this STM32 cube ID, it selects these GPIO for UART3. So here we can see clearly that our PB10 is UART-TX and PB11 is UART-RX. But now we have to consult the schematic of our development board to see where these are connected. So now let us open the schematic of our development board. So here I have the schematic of my development board, that is the Nucleo development board. And now let us see, analyze this schematic. Where is the UART lines? So here we have, so as we can see, this is our microcontroller, that is U8B, and here they have used PD8 and PD9. So here PD8 is the UART-TX and PD9 is the UART-RX. And here is the connection coming from our ST-Link part, the top portion of our development board. So it is going there. So the TX of our microcontroller is going to the RX of ST-Link, and this RX, that is the receive pin, is connected to the TX of ST-Link. So we have to configure something like this, that is we have to make PD8 as the UART3 TX. So let us note it down somewhere and then do the same modification there. So now let us go back to the IDE and find the pin PD8 and PD9. So here they are, PD8. So we have to make this pin PD8 as the UART-TX pin. So here we can see the alternate option, that is UART3 TX. When we click this, this will go there, jump there. See, this has gone here. Similarly, change this PD9 to the UART-RX pin, that is the UART3 RX pin. Now we have properly configured the UART. Now let us configure the main peripheral, that is the Ethernet. Now let us configure the main peripheral, that is the Ethernet. It will also be found inside this connectivity section, ETH. So here we have to enable our ETH. So the ETH MAC, the ETH peripheral of our STM32, it supports two connectivity mode. So the first one is the MMI, or the standard mode. So this MII, this stands for medium independent interface. You can search this on Google also. So this interface is used to connect the output of MAC layer to the file layer, actual file layer, the physical layer. So there are two modes available. One is the MII mode, or the medium independence mode, or reduced medium independent interface mode. So this one is used inside bigger motherboards, bigger processor, like in our PCs or laptop. And there is the alternate version, that is this reduced version, and this is mostly used inside embedded systems. So these use less so this mode, that is the RMII mode, this use less number of GPIO pins. That is why this is more suited to embedded applications, small applications, compact applications. That is, but our STM32, it supports both modes, so you are free to connect both types of Ethernet MAC to this chip, our STM32 chip. But in our current development board, they have used a PHY chip which uses this connectivity option, that is RMII mode. And you can get the details from the datasheet or the user manual of our development board. So now let us open that. So now let us select RMII here, and as you can see that the IDE has enabled some of the pins here, and these pins will be connected to the PHY chip. So now let us zoom to this area. I will reduce the size of this pin, something like this, or I will minimize this using this button. So I have minimized this. So here at the bottom area we can see the pins, the Ethernet pins. So what are the pin? Here we can see that they are prefixed with this thing, that is ETH. So the first pin is ETH MDC, ETH reference clock, ETH MDIO, ETH CRSTV, ETH RxD0, ETH RxD1, ETH TX enable, TXEN, and Ethernet this TXD0 and TXD1 pin. So these are the pins that will be connected to the PHY chip. So here we can see the development board, and here is our main IC, the main microcontroller, or the STM32 F439. And below this main microcontroller, here we have the Ethernet PHY area. So this one is the PHY chip, and this PHY chip is connected to the main microcontroller using the RMII interface. And here we can see the zoomed image of this PHY chip, and from here we can read the part number, that is 8742A. So if you search this in Google, you will get the data sheet just like this. So this one is the chip 8742A. So this chip is currently produced by the company called Microchip. This company is popular for producing the PIC series of microcontrollers. But actually here you will notice that there is no microchip branding here, but you will see the branding as a SMSC. So this is actually the company, this was the company which was producing this chip, and Microchip acquired this company, that is SMSC company. So this was a smaller company. Microchip purchased this company entirely. In the same way, they have purchased Atmel also. The Atmel company is popular for producing the AVR or the 80 mega series of microcontroller, which is also used in Arduino boards. Now I will go to the schematic of the development board here, and I will open the Ethernet section like this. So here on the extreme left we have the signals coming from the microcontroller. These are the signals coming from the phi output of the microcontroller, and here we have our phi chip, that is the LAN8742A. This is the same chip, this chip 8742, and here in the schematic we can see that it is U9, and here also you can see that it is labeled U9. So this is the chip, and the output of this phi is going to the, this first it is going to this Ethernet transformer. This is U11, this is the Ethernet transformer. We can see this here, this one. Let me zoom here. This one is the Ethernet transformer, actual Ethernet transformer. So if I zoom here, you can see the part number also, KMS1110, and this one is U11. And let us go back to the schematic. This is KMS1110 and this is U11. And finally the output of this transformer is going to this CN14, and this CN14 is the actual RJ45 connector which is used to connect to the Ethernet. And here we can see the designator, it is CN14. And if we go to the, here you can see that this is CN14 here. So this is the RJ45. Here we plug our LAN cable like this. So what we have to do here, we have to make a list of all these pins that is used for interfacing this phi area. So let us begin. I will open a Word document like this, and I will create table here, and I will here I will feed the name of all the signals used. Okay, so I am feeding this name of these signals. So let me open this side by side. Let me try to open this side by side. Perfect. So the first signal is this TX enable. I have TX enable here. Then I have TXD0, TXD0. In the same way TXD1, TXD1. Then RxD0, RxD0. RxD1. Here we have RxD1. Then this CRS div, this CRS div. Then MDC and MDIO. So MDC and MDIO both are present here. And then I have the reference clock also. It is here, the reference clock also. Now the second thing what we have to do, we have to get the mapping to the MCU port. So it is also written here in the schematic. So in the second column of this table I will put these things, like this TX enable signal, it is actually available on the PG11 pin of the microcontroller. So this PG stands for port G pin 11 or bit 11. So I have put that in the table here. In the same way PG13, 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 PB13, then PB13, PC4 and PC5, PC4 and PC5, then PS7, PS7, PC1, PC1, PA2, PA2, PA1 and PA1 finally, like this. And now the third thing that we have to do is to go to the cube ID and then match whether the pins that that have been assigned by the ID is correct or not, means it is matching our current hardware or not. So you have to go to this, then you have to open these two things side by side. From here you have to match it. Like here we can see that the Ethernet reference clock is on PA11. So let us go to our document and see that this one is like it is reference clock, it is on PA1. So So here we can see in the cube ID that Ethernet reference clock is on PA1. In our document, it is also in PA1. So I will write checked OK here. In the same way, I will check the other signals. So if you go on checking the signal, you will find that two signals are not matching. Two signals are not matching here. So now let us see where is the mismatch. So mismatch is in these two pins, that is TXN. So now let us see where it is TXN. So TXN is here on PB11, but on our table if we see that our TX enable should be on PG11. So let us change this PG11. Okay, so where is PG11? So PG11 is here, but currently our cube ID, it has assigned this TX enable here on PB11. So this will not work in our board because in our actual hardware connection it is on PG11. So here we have to assign this signal, that is Ethernet TX enable. Done. See, in the same way we have to change this second mismatch also, that is we have to change the position of this TXD0 to PG13. So where is our TXD0? TXD0 is here on PB12. It won't work. It should be on where? It should be on PG13. Where is PG13? Here is PG13. TXD0 we have to assign here like this. Now it is fully compatible with our hardware. Now here we have to do one important setting, and this is the Ethernet MAC address. So here we have to feed the MAC address, and this is 6 bytes long. And I already have a dedicated video on how to obtain a valid MAC address. So just go and refer to that video and get your own this MAC address and enter it here. So or just enter the MAC address which I am using for testing purposes. So this one is in hexadecimal. This is 80342874 A5 and CB. So that's it. This much setting you are required to do in the ETH section. Now we need to add FreeRTOS support to our project. For this, first minimize this section, connectivity, and go to the middleware section here. And from here select this option, that is FreeRTOS. And by default it is disabled. And here we have to enable it, and we have two different options. One is the CMSIS version 1 and version 2. So we will go with this version 2, and this CMSIS, it stands for Cortex Microcontroller Software Interface Standard. So this one is just acting like a abstraction layer here, and using this interface we are accessing FreeRTOS. So what is the advantage? That we can easily change the underlying operating system to a different version, to a completely different operating system. That means we can switch to some other operating system from FreeRTOS, and but will our user level code will not change, because this CMSIS version 2, this will act as the abstraction layer for operating system, and this is the standard developed by the ARM, the company which is producing the core of this microcontroller, that is ARM Cortex M4. So this is not actually the FreeRTOS, but the interface that is used to access FreeRTOS. So in this cube ID, we don't directly call the FreeRTOS function, but we use this helper, that is CMSIS. And there are two versions currently available. One is version 1, and this one is the latest version. So we will go for this version. And then we have to configure the actual operating system, that is FreeRTOS, and the configuration is displayed here. So let us see what we have to do here. So from here we can see that the actual underlying operating system, the FreeRTOS version is 10.3.1, and we will keep the MPU and FPU disabled. Make sure that this use preemption, preemptive, this is enabled. This is also the default option. Then tick rate is 1000. Minimal stack size 128 words. And the default memory allocation scheme is dynamic, and we will use the memory management scheme heap 4. Make sure heap 4 is selected. You have to consult a dedicated course on FreeRTOS if you want to understand what does this mean, or you can refer to the FreeRTOS website or their reference manual. But I assume that the user is familiar with FreeRTOS, so I am not going in the details. Rather, I am focusing on this STM32 and Ethernet configurations. And for debugging purposes, it is better to enable one of these stats. All other default settings are okay. And then we have to go to this area, that is advanced settings, and here we have to enable this thing. This one, use new lib re-enterant, and by default it is disabled, but we have to enable it here. And one more thing, uh, in the stack section, go to the config parameter section. This one, record stack high address, this should be enabled also. This will help you in debugging. This will help us catch any stack overflow, and we can also we will also be able to view how much stack each thread is using. That is why start this, and that is why enable this uh, record stack high addresses. And as we all know that the FreeRTOS operating system, it help us divide the complete our embedded application into several independent and parallelly running threads. And the very first thread that this configurator, this STM32 cube ID create for us, is called the default task. And this default task is automatically created when you create a new FreeRTOS based project, and you can configure it from here, that is task and queue sections. So here we can see our default task. So from this area we can configure this task, that is our default task. Here is the default task. So what we have to do here, by default the stack size which is allocated by STM32 cube ID is very small for this default task. We cannot run a TCP/IP based application with such a small stack size. So what we have to do, we have to increase the stack size here, and by default it is 128. That means 128 words, and the word size of this microcontroller is 4 bytes or 32 bits. So let us change this and change this to about 512 bytes, or not byte, 512 words. So that will be in, if you calculate in bytes, it will be 4 times, that is about 2 KB. That's it. This much setting is required in the FreeRTOS section. Now we have to do one more important configuration, and this is the configuration of this Ethernet peripherals interrupt. So go to this section, ETH peripheral, and from here go to the NVIC section. So this NVIC stands for Nested Vectored Interrupt Controller, and you must be familiar with this term if you are programming in ARM environment. And using this cube MX we can easily enable the interrupt line, and here it is, the Ethernet global interrupt. We have to just tick this one and it will enable the interrupt. The default priority of 5 is okay, so we will not change this. Don't check this one, we don't need this. Just the Ethernet global interrupt is required. One more setting we have to do, and this time we have to go to this NVIC section here, and this NVIC section is under this system core here. So this is the actual interrupt controller which is present inside all ARM microcontrollers, all ARM based microcontrollers. And here we have to manage the code generation, and here we have to go to this section, that is the code generation section. And here you can see the list of all the interrupts. Just find our interrupt, that is Ethernet global interrupt. And let me expand this area a bit so that we can clearly view these columns. Our chip image is getting shorter, smaller and smaller. We need to view all the label of these columns to understand everything properly. Now we can clearly view all the column headers. So by default this cube MX generates the IRQ handler, but here in this project we don't need this handler, because this handler will be blank and will not do anything, and it will expect that user put some code into it. But this is not the way. Our Mongoose, the Mongoose web server and its integrated driver, they already come with this interrupt handler, and we will use that one. We will not generate and use the this IRQ handler which is generated by our cube MX. So that is why we have to remove the check mark here, like this, Ethernet global interrupt, and we have disabled the generation of IRQ handler. So let me show you what is the difference here. So first let us enable this one and generate the code. First save the project and then generate the code using this generate code button, and it is generating the code, the C code. Let it finish. Now it has completed generation of the codes. So when this check mark was not cleared, it was tick, that is true, generate IRQ handler. So in this case, if you go inside this core and then source and then this file STM32 F4XX IT, this IT stands for this interrupt handler. So here you will see, so this file contains the interrupt handler for all the enabled interrupts. So here you will find that this one is our IRQ handler for the ETH peripheral, that is the Ethernet peripheral, and it is doing something like this. but this code will not work because this one is delegating the task to our the HAL drivers. We don't need this method. We have to use the interrupt handler that is provided by the Mongoose web server and its associated drivers. And if you go here again, and this one, this check mark, it generates the code for this IRQ handler. And this second one, this last column, if we tick it, it will use this default handler that is provided by the HAL library. So let us uncheck this one. If we uncheck this one and then regenerate the code, let us see what happens. So what will happen, it will remove this one. This handler will be there, but it will not be delegated to this HAL library. So let us save all and regenerate the code, and let us see what happens. See, this time it has generated this handler, IRQ handler, but it has not put the HAL default handler here. So this is the function of this column. And finally, let us get rid of this handler. So now uncheck this, that is generate IRQ handler, remove this tick, save the project and regenerate the code. And let us wait. Code generation completed. Let us go to this interrupt handler file, which is here in the src, this one _it.c. Scroll down, and here you can see there is no handler for the Ethernet peripheral. There is handler for TIM6, debug monitor, and the internal ARM cores interrupts like uses fault, bus fault, but not for the our interrupt handler. So this is great. This is what was required. Now let me show where is the actual handler within the driver code. So let us go to the Mongoose distribution. Here is the Mongoose distribution which I have cloned from GitHub, and go to this directory, that is src, or the source directory, and inside this you will find a subfolder called drivers. Now let us open this folder, drivers, and here you will find codes and file for all the Ethernet controller which are supported by Mongoose. So we are interested in this one, that is STM32F series. But please note that there is also one STM32H. So don't open this one because this is these are for the H series microcontroller, which are the high performance microcontrollers. But we are currently working with this F series, so just open this one. And here try to find the interrupt handler. If you search for the term IRQ, you will find it very easily. So here is the actual Ethernet handler. You can see. So inside this file, that is STM32F, we have the actual handler. This one. So this code will handle the interrupt properly. So we don't have to worry much about it. Just for the information, I'm showing you where is the code. So here is the code, and you can match it. The name is proper. That is eth_IRQ handler. So how to check the name of the interrupt handler? See, just go to your STM32 cube ID. So here is a assembler file, and it is called the startup file, and this has the default handler for all the interrupt source that are present inside that microcontroller. So here is the list. So here is the list. So these are actually the weak functions. So by default they have default implementation which does nothing, and if implementation is provided by the user in the user code, then that one is used. So here you can find the name of various interrupt handler. So let us do a search for ETH. So here it is. So the name is eth_IRQ handler. Same name is used here, eth_IRQ handler. So when the user is providing the implementation of this weak function, then this implementation will be used. Now let us add Mongoose support to our project. For this, go to the Mongoose distribution folder, and this is what we have cloned from GitHub repository. And here are two main files, this one, the mongoose.c and mongoose.h, and these two file contains the entire mongoose framework. So this contains the top level web server, the middle level TCP IP support, and the lower level driver support. Everything is there in these two files only. So adding support is extremely simple. So let us start with the source file, that is mongoose.c. Just click and drag it and drop it here inside the src folder or the source folder, and select the option copy files and click OK. And here it is, Mongoose in our project. Next we have to copy the header file, and this is mongoose.h. In the same way, click and drag it, but this time drop it in the inc folder, this one, which stands for include files, like this. Select the option copy file and hit OK, and here it is, mongoose.h. So only adding these two files add the entire Mongoose system to your STM32 project. That's it. But please note that we don't have to copy any of the files that are provided inside this source folder. So these are for development purpose only, and I have already told that the contents from these files are already amalgamated to these two files using some amalgamation tools. That is why we don't have to copy any of the file. And just few minutes back I have shown you the drivers, the driver for the STM32F. These are also included inside this file. If you do a search here, mongoose.c, you will find the content that is present inside that driver file, that STM32F driver. So just click here and do a search like this, STM32F, and you will get the content of this file. So these comments, this no, from here we can get the idea that from now onward the contents from this file, that is src driver STM32F, are following these lines. So these are the contents from that file, and we can also see the end somewhere down. So here it is terminated and the new file started, and this one is for STM32H. You can also compare the contents from here to this file. You will see the contents are same, this F file. Now let us configure Mongoose to our platform. As with any embedded library, we have to configure it according to our platform, then only it can run on it, because these embedded libraries are designed to run on a variety of platforms. They can run on different microcontrollers, they can work with different Ethernet controllers. So that is the main aim of those libraries, to reach as many users as possible using various different platforms. So let us begin the configuration, and all the configurations are done using preprocessor directive, and we have to pass this preprocessor directive, and we have to pass all this preprocessor directive directly using the compiler flags. So we will just right click on our project here and go to the properties option, and then from the C++ build section, go to the settings section, and here after this GNU GCC assembler we have GCC compiler, and here is the preprocessor. And from here, using this GUI, using this dialog, we can define some preprocessor directives or symbols using this plus button. So using the very first configuration, we will tell Mongoose that we are running on a ARM processor and we are using the CMSys operating system that we have configured. So just open your web browser and go to mongoose.ws, and from there go to the documentation, and here go to this section, that is build options. So here you will find various build options. So from this list we will find our platform. The first one is for Unix, second one is for Win32, and then we have ESP32, ESP8266, and we have option for FreeRTOS, and we are, as we are using FreeRTOS, we can use this option, but we will use this one because we are using this SimSys RTOS 2 as our abstraction layer, and this is also applicable for FreeRTOS and also for this operating system, that is Keel's RTX 5. So first just copy this and we will paste it here. And this MG, this stands for Mongoose. So all the things are prefixed with this, all the Mongoose things are prefixed with this MG. So this select architecture equal to CMSys OS RTOS 2 API version RTOS 2. This is already discussed before while we are creating this project, STM32 cube project. So we have done with the first configuration. We have to do few more configurations. Next we have to tell Mongoose which Ethernet controller we are using. So it supports various different kinds of Ethernet peripherals, and from there we have to choose one which is present in our current platform, our current board. So since we are using the Nucleo board and we are using the internal, the built-in MAC of this chip, that is STM32 F429's internal Ethernet peripheral, and that is done using this one. So we have to set MG enable driver STM32F equal to 1. So this will enable the STM32F inbuilt Ethernet peripheral support. Just copy this one and in the same way add this here, MG enable driver STM32F equals 1. And one more setting we have to do, and this one is to enable the inbuilt TCP/IP stack of Mongoose. So Mongoose can either use an external TCP/IP stack or inbuilt TCP/IP stack. So in case we are running Mongoose on a platform like Unix or Win32, then it will use the TCP/IP stack that is provided by the underlying operating system like Windows in case of Win32, or Linux or Unix in case of this thing, architecture Unix. So sometimes there is a TCP/IP stack present in the operating system or our platform, then we can directly use that TCP/IP stack. But if our platform does not include a TCP/IP stack, then this Mongoose also has its own inbuilt TCP/IP stack that we can use. And to enable that TCP/IP stack, we have to use this option. From here we can enable various different type of TCP/IP stacks. So the first one is LWIP. Later on I will show you how to use LWIP also, and it also support FreeRTOS TCP/IP stack, but we have to use this one, that is enable TCP/IP. So this one will use the internal, the built-in TCP/IP stack of Mongoose. Just copy it and paste it here. So we have done various basic configurations. So only this much setting is required for this basic project. This is enough to run a sample and try out this great open source embedded web server. So now let us start writing the application code. And our very first application will be a simple, super simple web server, and this web server will return OK for any request. And this simple application will help us test our hardware and the basic software setup. So once you got this running, we will then jump on to creating great and interesting application using this Mongoose library. But before this, please give me a like on this video if you want to inspire me to create such informative videos in the future, the videos that are related to advanced embedded systems. So please give my video a like. So now let us open this main.c file, and here we will start writing our application code. And the very first thing that is required is to include the mongoose.h header file. And put it inside this user section, so that when we regenerate the code, these lines are not overwritten by our IDE, that is the STM32 cube subsystem. And then we have to go to the default task. And as we all know that in a free RTOS or any RTOS based, our entire embedded application is divided into small tasks that execute parallelly in the CPU using preemptive multitasking. So this default task, this is the first task that is created by default by this STM32 cube ID, and we should place all our code here. This is the very first task or thread that is started on a STM32 based this free RTOS based environment. So here we will first initialize our Mongoose library. But before that, let us do a very important thing, that is to redirect the output debug output to our UART3. That in that way we will be able to easily view what Mongoose is trying to tell us, and this will be very helpful if something does not work and you want to find out why it is not working. So we can directly view at the logs that is sent by this Mongoose, because this is a very big system. So to debug this we need those logs. So let us redirect the logs from Mongoose to our UART. For that we have to create a function like this. Here it is, the function, the log fn. So this is the logging function. Just create it in your project after all the default STM32 codes. We have to put it in the user section or it will be deleted. User code begin for before default start default task. So here we have some user code section, we will put it here. It is important to put any user code that we are adding inside these tags, these comment tags, user code begin and user code end. Otherwise if we regenerate the code from STM32 cube, like for example we wish to change some setting using this IOC file, opening the GUI, and if we regenerate the code, then our code will be overwritten. So to prevent our codes from being overwritten, we have to use these sections. So what this function is actually doing, this log function, it has two parameters, one is void param and one is ch. So only this one is interesting. Through this function, our this Mongoose system, it will send us characters that we have to redirect it to UART3, and this we will do it using the HAL function. And I will not discuss this function in detail here because the user is expected to be familiar with this system, that is the HAL driver libraries of this ST microcontroller. So here we are using the instance that is UART3, and we are using this UART3 because in our this development board, the Nucleo development board, this is already connected to the inbuilt USB to serial converter. So it is very easy to use this port for debugging. We don't have to use any external USB to serial converter or USB to TTL converter like FT232 or PL2303, something external like that, because it is already inbuilt into the ST-Link portion of our development board. And then we pass this character. We first cast it into a UINT8T pointer, and here is the length. So we are sending a single character at a time, that is why I am using one here. And this is the timeout. We will use 1 millisecond timeout, that's it. But still we are not done, we have to connect this function to Mongoose. So how to do that? It is done using this function, but before that we will create the main manager structure of Mongoose. So the first object or the structure we are having is of type mg manager, and this stands for Mongoose manager, and we are using this variable name mgr simple. Done. We have created. So this manager is important for all this Mongoose based application. So the very first variable that we should declare is the manager, and then this second line of code, this mg log set. So we will, for debugging purposes, we will increase the log level and we will use the debugging level. You can decrease the log level, means if you want to view lesser number of messages, so this will print each and every detail whatever is happening inside the Mongoose subsystem. So in during debug phase we will use the log level of debug, and then we use this function mg log set function. So this will attach our newly created log function with Mongoose library like this. So here we have a log function, we are using a function pointer and we are passing it to. Now this Mongoose subsystem will store the address of this function, and from the future it will use this function to send character to the UART. The next thing, we have to initialize this manager before we can use this. So for that we have to use this function. It is mg, that stands for Mongoose, mgr, that stands for manager init, and we have to pass the address of this structure using this sys address of operator. So this will initialize our manager. That's it. So the initialization is super simple, and next we can move on to our code that is related with the actual HTTP server. And the first line will be to start listening from incoming connections from the clients or the browsers. So here it is, this line we have to call this, and this is mg. So all the Mongoose functions are prefixed with this thing, that is mg, which stands for Mongoose, mg underscore http listen, and the first parameter is the address of our manager, Mongoose manager, and then we have the URL. So the next parameter, here we have to specify how to listen, and I will describe this in detail later on, but for timing just put it like this, that is 00000, and after this colon, this is the port number where we have to listen, which TCP port number our server will listen. So for this basic example we will use port 8000. So during accessing this web server we will use this same port number from our web browser. But don't get confused with this 000 IP. I will tell you more about this. This is not the IP address of this system. This is a special IP address that I will discuss later on. And the next one, this fn, this is our callback function. So this Mongoose is a callback based system. It will, and the last parameter will be null. And if you want to know more about this function, just go to the Mongoose documentation and search about it. And the next thing, we have to put this code inside this infinite loop. So this is called repeatedly, and the name of this function is mg underscore mgr poll, that means poll the manager, and the first parameter is the address of our this main manager. So this is the main function that does all the processing, the input, the output, everything is managed by this function. So you have to call this function repeatedly. So that's it, this much code is required here. Now we have to create one important thing, and this one is the event handler for this listener. And next we will do this. To write the event handler or the callback function, let us first go to the Mongoose website, and here is the documentation section, and in the documentation please go to the tutorial section, and here we have various tutorials. Right now we are interested in HTTP, so let us go to the HTTP section, and we will begin with writing a HTTP server. So we will go to this section, HTTP server section, and here the first example is a minimal static server, but we will not use a static server, because the static server serves files, static files, HTML, CSS, JavaScript file, which are stored in a file system. So in order to run this static server example, we will need a file system, either a real file system or an embedded file system. But right now we don't have any file system in our embedded board. That is why we will go with a dynamic RESTful server. And here we will copy this example of callback. Let us copy and paste it just above the logging function. So this is our main event handler or the callback function, and here we have different parameters. So this function will be called by the manager whenever there is a something interesting in our web server. So this will be called. For example, when there is a incoming connection from a client or a browser, then this function will get called. So the first step is to check what is the cause of the event. So here we are comparing this variable which is of type integer, and we are checking if it is an HTTP message event. So in that case we will use this function, that is mg HTTP reply, and we will reply to this connection. The pointer to the connection is passed to the callback function, and here is the status code. So since we want to send success, so in HTTP this 200 stands for success code. And then we put a content type. This is the HTTP header here, and the content type is plain text, and this is the body of the reply. And to explain that this function can take printf style formatting also, we have used the %s here, and this is the string that is will be replaced by this placeholder. So this is our very simple web server. So let us try to build this code. It's building. Oh, but we have some errors. It is not able to build properly. It is not able to compile. So now let us see what is the problem. Actually, I have done one mistake. Just go here, right click here, go to properties, go to C++ build, and then setting. Here MCU GCC compiler, and here preprocessor. Here the mistake is this. This is not the proper way to select the platform. We have to write something like this: mg underscore arch equal to this variable, this thing, that is Simsys RTOS 2. This is the proper way to select the architecture. Apply and close and build once again. Now everything is fine. We have 0 errors and 0 warnings. That's great. Now just take out your Nucleo development board and connect it with your PC using the micro USB cable, just like this. And here we see the power LED, that is this green LED glowing, and also the power section of this ST-Link module is also glowing red, and this one is glowing red, and this one is glowing green. So now our board is ready. We can download the program to this chip and try to run and execute the program. So now let us hit the debug button, and it is starting the debug session, waiting for debugger connection. And now it is downloading the program to the flash memory of our microcontroller, which is present in our development board. You can see the messages here: erasing flash memory, download in progress, verification, download verification successfully. And now the debug session has started, and here we have our run cursor in the very first line of our main function. This is the very first executable line in the main function. Now we can resume or run our code using this green icon, and the keyboard shortcut is F8. But before running our code, let us first start our terminal program. So here I will use real term. Go to the port section and select your USB to serial converter. Enter proper baud rate, and you can confirm the baud rate from here, from the main function. From the main.c file, the uart init, Here you can confirm the baud rate. We have 115200. So we will use the same baud rate here, and we will also increase the display size. We will increase the row number from 16 to 40, something like this, and we will restore this window. We will make the size of this window smaller and put them side by side so that we can view the content of both the windows like this. Make sure the port is open, and now we are all ready to hit the run button. And here we go. And here you will see all the outputs that are sent by our Mongoose system. And right now it is telling us that network is down. This is because I have not yet connected my Ethernet cable. So now let me plug the cable, and here it is. You can see as soon as I have plugged the cable, it has detected the link and it has sent the DHCP request, and we have also received our IP address from the DHCP server, and it is 192.168.1.33. So we will hit this IP address from our browser. So now let us open our web browser. So here is my web browser, Firefox, and let us enter this IP address http://192.168.1.33, and after this colon symbol we will put the port number, and right now we are listening on port 8000, that is why I have entered 8000 here. So now let us hit enter. 1 2 3 go, and here we have the response from our embedded web server. That's great. So when a client connects to Mongoose, it is also reported here in the logs. We can confirm that. So if we go to the web browser and refresh this page, uh, let me restore this web browser like this. Clear the logs and let me refresh once again. So just go to your web browser and click Ctrl Shift and R. This will force the refresh. And here you can see that it has accepted a connection from 192.168.1.36, and this is my this desktop PC. So finally, after approximately 1 hour of hard work, we have finally got Mongoose up and running, and we are now all ready to create all sorts of interesting application that Mongoose is capable of. We will create full device dashboard. We will read sensor data from our microcontroller and display them on our web browser using a web interface. We will control various devices using the web browser, and this Mongoose library, it has lots of functionality inbuilt. We will see how to pass JSON, how to perform Ajax request, how to connect using web server so that we can stream live data to our web browser. We can plot live graphs, lots of interesting stuff we can do because this is a professional library, but it is also open source. So this is a great. In the coming week we will create lots of interesting and professional application using this Mongoose web server, so stay tuned. So I believe this video must have helped you. If this is so, please like the video and subscribe to my channel. Thanks for watching. See you in the coming videos.